Conversion of context-free grammar to push-down automata. We will be given with a context-free grammar. We have to convert its equivalent push-down automata. That is, the language accepted by context-free grammar should be equal to the language accepted by the push-down automata. That is, the strings in this language that is accepted by this grammar should be equal to the strings in the language that is accepted by this push-down automata. If some x belongs to L of G, then the same x should also belongs to L of M. That's what equivalence means. So we are going to convert a given context-free grammar to its equivalent push-down automata. The steps involved in this is, first we need to convert the given context-free grammar into Gribach normal form. Next, we need to include the start symbol transition. That is, for the start symbol S, we need to include this transition to push the start symbol inside the stack, and the initial state gets transferred to the state Q1. So this is the first transition we have to do in all the conversion. That is, whatever is the start symbol, that start symbol we have to push it inside the stack with the help of this transition. Now next is, we know that when any particular grammar is in Gribach normal form, then we will have the production of the form single non-terminal followed by single terminal followed by 0 or more non-terminals. Suppose you have the production of the form non-terminal followed by 0 or more, let us assume more than one non-terminals we have. So in that case, we have to include from Q1 this terminal symbol you have to add here, and this non-terminal symbol you have to add here. Right hand side of the transition should be, the move should be Q1 comma whatever production we have to include it here. Okay, suppose if rule number 4 is, suppose you have the production of the form non-terminal tending to terminal, then Q1 comma this terminal symbol, then this non-terminal should come here. The right hand side, the move should be Q1 comma epsilon. And finally, we need to include accepting state transitions. There are two accepting state transition, one for final state method. This is for final state method, and another one is for empty stack method. So for final state method, there is a state transition. Now Q2 is the final state here. Now in empty stack, we are just emptying this stack. We are removing the bottom of the stack, so it is represented with the help of epsilon. Now we'll take one example. We are given with a set of productions in the grammar G. So this is our set of production. So what is V is S comma B comma A is set of non-terminals. What is set of terminals here? A and B. S is the start symbol. S is the start symbol. We are given with this grammar. We need to construct it equivalent push-down automata. So we will first try and include, S is the start symbol. So we will include the start symbol production. See, it should be in Gribach normal form. We'll check whether it is in Gribach normal form. Yes, it is in Gribach normal form. So terminal followed by non-terminal, terminal followed by non-terminal, terminal followed by non-terminal. Single terminal is also allowed. 0 or more occurrences of non-terminal is what is Gribach normal form. So it is already in Gribach. This given grammar is already in Gribach normal form. Second step is, we have to include start symbol production. So what is start symbol production? Q0 comma epsilon comma Z0 is equal to Q1 comma SZ0. This is what is start symbol production. I am not doing anything. I am just inserting whatever is the stack symbol. If our start symbol is some B, then we have to push that B inside this S, inside the stack. That's all. Here our start symbol is yes. So I have applied rule number 2. Here in some book they will be referring with lambda. It refers only to epsilon. So Q0 epsilon comma Z0 is Q1 S Z0. So I have just introduced the start symbol production. Next is, we will take each and every production and we'll try to construct its equivalent transition. So we will take S goes to AB first. So this comes under rule number 3. So S goes to AB. Instead of this is S goes to AB. Now if that is the case, what production we need to include? We have to include like Q1 comma terminal, you have to include A comma this right hand side of the production, that is S is equal to Q1 comma B. So if you have a production non-terminal tending to terminal followed by non-terminal, then you have to include like Q1 comma terminal comma non-terminal is equal to Q1 comma non-terminal star, whatever may be, you have to include it. So we have included like this. So this is Q1 comma, this is the non-terminal we have, so A we have included. The right hand side should come here. So right hand side is S, so S is coming. Now left hand side Q1 comma whatever is in the left hand side, that should come. So B is coming. Likewise you have to introduce for the next one, that is B goes to BA. So B goes to BA is Q1 comma B comma capital B is equal to within bracket Q1 comma capital B. I'm sorry, Q1 comma A, right hand side you have to include. This one you have to include. Okay. Now what about the next production? A goes to capital AB. In that case Q1 comma small a comma right hand side capital A is equal to Q1 comma left hand side B should be there. And you have one more production, that is B goes to small b. This comes under rule number 4. What is rule number 4? Right hand side you have to include epsilon. So if you have delta of, you'll be having delta of B comma capital B is equal to Q1 comma epsilon. And finally you have to, this is start symbol production. First one is start symbol production. Okay, and for each of the production we have included 1 transition, and finally we have to include 2 transition for accepting state. So we'll be including like Q1 comma epsilon Z0 is equal to Q2 comma Z0. This is for final state method. And delta of Q1 comma epsilon Z0 is equal to Q1 comma epsilon. This is for empty stack. Now the first production and the last 2 production will be same for all the conversions, and the remaining production will be varying depending upon the first transition and the last 2 transition will be same for all the conversion, and the remaining transition push down automata transition will be based upon these production for the given grammar. So from this we can construct PDA M of what is Q here, Q0, Q1, Q2. Set of states is Q1, Q0, Q2. Set of input symbols is A comma B. Set of stack symbols is A comma B. Delta is defined here. What is the final state? Final state is Q0. Initial state is Q0. Final state is Q2. So we have defined with Q, sigma, gamma, delta, Q0, F, 1, 2, 3, 4, 5, 6, and another one bottom of the stack, 7. So this is what is the corresponding push down automata we have designed. So the language accepted by this grammar will be equal to the language accepted by the push down automata. So we have constructed a equivalent push down automata, this being the set of transition for the given grammar. Now you please try some more problems and see whether you were able to convert this push down automata, construct push-down automata from the context-free grammar. So you try these problems. S goes to ASBB or ABB. So these are capital BPs. This is first problem. Second problem, S goes to 0BB and B goes to 0S or 1S or 0. So you try and convert this given context-free grammar into equivalent push-down automata by applying this 5 set of rules. So again, I have given the grammar only in Gribak normal form. The first step is over already. You can try and see the remaining steps. Thank you.